Yes, excellent. All right. So today we have Ann Gelb here to talk about empirical Bayesian inference using joint sparsity. Ann is a full professor at Dartmouth College in the math department, and is well known for her work in PDE, inverse problems, Fourier analysis, computational Fourier analysis, and a wide range of other interesting topics. And so I am very happy she agreed to come here today, and I would love to turn things over and hear what you want to talk about, Ann.
Okay, thank you. I want to give you a little bit of a heads up. I did get my second vaccine yesterday, so I'm feeling a little off. So hopefully that won't change the talk too much, but we'll see. Maybe we'll just have to tell some jokes to keep it going. I'll try to keep an eye on the chat, and we'll see what happens. I just want to tell you that this is pretty new work. We just submitted this paper within about a month ago. So there could be some kinks, and I'm always looking forward to hearing what people have to say and the feedback. Okay, so I want to first acknowledge my collaborators. I don't play favorites with my students. I see it was very nice to have some of my students there. It's my seminar today, so thank you for coming. So this is with a former PhD student, Theresa Scarnati, who's now a full-on equal collaborator. She was at the AFRL for a long time, and now she's joined Qualis Corporation in Huntsville, and she actually lives in Huntsville. Even though she's doing the job remotely. And the other is Jack Zhang, who kind of brought this problem to us. I was really impressed with that when he was an undergraduate at Dartmouth, and he's now a PhD student at the University of Minnesota. And of course, we're very grateful for our support from different agencies that are listed here below. Okay. So the motivation for this problem is something that I've been thinking about for quite a while, thanks to some of the people that are actually here as well. I've worked quite a bit with Doug Cochran on these types of problems. And it's from Spotlight synthetic aperture radar. So this is just a little cartoon of what a SAR system basically does. And how it collects information over a scene of interest. And the idea is to try to reconstruct the underlying signal from the data that we collect. And the reason, and it's synthetic, because by using these sort of multiple observations from a small antenna, you can synthesize the effect of a large antenna, which allows you to have enough resolution to recover the scene, because you can't put an enormous antenna on your plane. So that's the motivation for the problem. But I'm going to, so if you're scratching your head later and say, yeah, but you haven't actually solved this problem. Well, we're still at the beginning, but that's where we're going with this research, is to try to tackle that problem in particular. Okay, so a lot of people in this audience are very familiar with SAR, but just to have a kind of the slide on what's the underlying physics behind it, is that basically you send out the signal. Can everybody see my mouse okay? Is that good? All right, Mark is in my view, so okay. So you send out the signal, it's a wave equation, you recover something from, and then you try to, and this signal is mixed, and that mixing sort of leaves you with some sort of transformation to Fourier data, and then you try to solve this inverse problem to recover the underlying scene. So that's the problem. The model is slightly different, of course, and we have to make some assumptions to actually have a model that we can work with. So here are the underlying assumptions that people make about far field SAR. First, that it is far field, or spotlight SAR in particular. So first is that the chirp rate has to be small enough, and that's so that we can do this demodulation in an effective way. This is what allows us to get an inverse problem that we can solve. And this is a reasonable assumption. The second assumption here is that it is indeed far field, and the far field means that you have plane waves. So instead of some kind of wavefront curvature, so you can neglect any kind of curvature of the waves. That's also a fine assumption in far field SAR. And the third assumption is that you only have isotropic scatterers, which means that regardless of the direction that you're coming from, you see the same reflection, you see the same scattering. Okay, that's a terrible assumption. It's completely not true. And the fourth is that there are no scatterers outside the ground scene. And that's also fine for what we've seen. And the fifth is that you actually know where it is that you're sending the signal from, which means that you're able to measure the round trip time precisely. This is also not a particularly good assumption. And the error that you get from that is a phase error, and you have to typically people use autofocusing to recover that. And I have to give Mark and Aditya a shout out because with their phase synchronization, they helped us to work out this type of error, which is not the subject of this talk today, but if you're interested in this, I'd be happy to talk about it more. Okay, so these are the assumptions that people make for the model. And the model basically becomes something that we can work with in terms of an inverse problem by using the Fourier slice theorem. Essentially, and this group knows this very well, so I don't have to spend any time on it, is that you have a projection that's from the data that you collect can be written as this projection. And we also know that for that at any given angle theta, we have a Fourier transform of that same underlying image or function, however you want to call it, given a particular elevation angle phi. And this Fourier slice theorem allows us to relate these two things together. So that means that, in fact, the phase history data, which we collect, essentially looks like Fourier data based on these angles, given a particular elevation phi. All right, so that's the setup. And of course, it's more complicated than that, but for our purposes, this is fine. But at the end of the story, in terms of the model, is that you can view the problem as trying to recover an underlying image from incomplete Fourier data. And we have a lot of experience in those things because there are other applications for which this is also true. For example, MRI or ultrasound or things like that. The indirect data that you actually acquire can be viewed pretty well as incomplete Fourier data. The difference here, of course, is that the signal is complex. Of course, then there are constraints on the data, which means that you have to consider the acquisition trajectories, any kind of noise, different kinds of undersampling that may come into effect for the problem that you're solving. So each measurement, which we'll just call f hat for the Fourier data, it comes from some known angle theta, and then you end up with this very nice model that we understand quite well, which is that we're given this is an inverse problem. We're given this f hat. We model it by this discrete Fourier transform operator, and we want to recover this underlying image f, which we just write as in vector form here. You can imagine just just sort of concatenating all the image pixel values to make it a vector. So of course, those of you who know me well know already that I hate the part of this model because there's because of a mistake it right away makes, which is that f is a discrete Fourier transform, but really the data that we have come from a continuous Fourier transform. And so you already have all the errors associated with the Gibbs phenomenon and that kind of thing, which sort of gets swept under the rug in the way a lot of people approach solving inverse problems in general, when the way a lot of people like to call this inverse crime. But in reality, it probably doesn't matter that much often, because there's so much noise in the problem that the error that you make here is not that consequential, although it should be considered. The other thing that's important in SAR models that isn't true in other kinds of applications is that the underlying signal is complex. Which carries its own issues, which we'll discuss a little bit today, but not so much. Okay, I see there's a question in the chat. Why is F complex? Well, because there's the information from the scene has both amplitude and phase. That people are interested. There's information in the phase that people are interested in. Okay, so okay, thanks for the question. So what's sort of new, what we try to bring to this story is this idea of multiple measurement vectors, and that's going to come up in a variety of ways in this talk. And basically, the idea is that you have some additional information from the redundancy that you get from multiple measurements within a small aperture window. Ideally, right, if it's all taken over a short time window, the scene itself has not really changed in a short amount of time. So that means that, you know, things that that you would rely on in this data, if it's inaccurate, maybe at one time, maybe it's more accurate at the you know, very close by angle theta, and you can kind of diffuse some of the error that way. And that's sort of the theme of the research that we've been doing in these last couple of years. Okay. And of course, because these are numerical schemes we're talking about, we want whatever we do to be efficient, accurate, and robust. It's important that whatever results that we get, that they carry enough information that we can still use them effectively for downstream processing, such as classification or whatever the interest is, whatever for the practitioners. Okay, so it's probably good to have some kind of picture in your mind about what these sorts of things look like. So this is, of course, not a complex return. This just shows the magnitude of these scatterers. But this is a parking lot at the AFRL. And I honestly, I can't remember how these two things are recovered, probably back projection and FFT, but I would have to look. But so this is from a 360-degree all the way around aperture. And you could see there's a road, right? And then the different of these reflectors come from different parts, from different vehicles and different lights. And you'd want to be able to, for instance, identify that this is in fact a backhoe, or this is whatever kind of four-door sedan or something like that. So the problem can be quite complicated. So I don't actually know if this is maybe this is not true anymore, but certainly as of a few years ago, the most popular way to reconstruct a SAR image is to do something like a matched filter or back projection or NFFT or something like that. And those, we know a lot about how those techniques work, and they're very quick. So that's a positive for them. More recently, people have really invested more time into compressive sensing techniques because you know, because the problem is often underdetermined, and there's been a lot of success in compressive sensing techniques. Nevertheless, there's still issues with robustness, lack of automation, and efficiency. So there are still some issues that remain. But regardless, which ever kind of method that you use, you still have the underlying problem that your model doesn't really match the underlying problem very well, especially as your aperture angle increases. So there's some work to be done. And as a consequence of that, these reconstructed images have speckle, streaking. I just listed a bunch of problems that result from that. And what we'll do today, not for this particular problem, but is to see how multiple measurement vectors, redundant data, can help to alleviate some of these issues. The other issue is the problem is uncertainty, right? Because all of these techniques that I listed above only give point estimate solutions, but we know that there's a certain amount of uncertainty in these estimates, and it could be really useful to know how reliable our results actually are. So that's what motivated us to start using a Bayesian approach to this problem and to other problems before that. Okay, so that's how we're going to frame the problem now. So we're going to set up the problem in terms of these random variables. F is a known forward operator. It doesn't, for our research, it doesn't matter what it is, but we are going to, well, maybe it matters, but we're just going to consider it to be a discrete Fourier transform operator, because that's sort of our applications of interest. We're going to consider Gaussian noise. So it's complex Gaussian noise. And you would have a particular observation, as we saw before, that would be given for the SAR model in this form. Now, as I alluded to before, the key here that makes what we do advantageous is that we're going to exploit that we have multiple measurements, presumably of the same thing. So if they're close enough in aperture in where you are in this theta angle, the measurements are close enough. So this is not, I mean, we're doing it for this problem, but people have done multiple measurements for sampling problems for a while. And so this is not something new in itself, to try to use this redundancy in some way. Right, I also want to point out a couple of other things, because we don't do them in this talk, but the way that we designed our method, it's open to other types of data. So for now, we only consider the same source of measurements, just to sort of keep the computation simple, which means that we're only considering Fourier data. But in fact, this is not any kind of inherent limitation, and you could have this F be different types of matrices depending on the data. So you can like have optical information and Fourier information, or whatever, some kind of blurred information, whatever is relevant to your particular problem. And then of course there's some registration that has to be done. And the other thing that I would like to point out is that you don't really need multiple measurements. You can have one measurement, and then you could play around with how you process it. And from what we understand about numerical analysis and a convergence of different types of processing techniques, that actually works quite well. But I'm going to leave that for maybe another invitation someday, but just so you can keep that in the back of your mind. Okay, so, oh, it's already 1:22. I don't know what it says on Mark's microwave, but that's what I have on my watch. So
sounds right.
Okay, so the rest of this talk, I'm gonna do the following. So this just sort of helps with the story and how we progress to where we are today, and hopefully it's a good way to present the material as well. So we start off with how we use compressive sensing, and then we show how the multiple measurement vectors can be used to improve the compressive sensing. And then we moved toward the Bayesian approach. And with the thinking that what we were able to do with the multiple measurement vectors for compressive sensing is going to be useful when we go to this Bayesian approach. And here's my caveat is that for this last topic, the Bayesian approach, right now we've only considered real and one-dimensional signals. So, but we're working toward it. So if you don't see beautiful SAR images at the end, that's why. I see there's a question in the chat. Assumed to be independent. Yes, we are. Yes, we are assuming independence. Thank you. Thank you for pointing that out. Okay. All right, so before we go on with the method, and I know that this is again very familiar to this audience, but I'll do it anyway. To define what we mean by sparsity, and this is a pretty standard definition of what sparsity is, and how we set up this sort of standard form of the compressive sensing method. Which of course, again, this audience is very familiar with. So basically, if you're just considering a point estimate, if you're just considering a particular observation, which is say this vector of measurements, you can recover the underlying signal by finding the argument of this. Of what's inside here in brackets. This L is some kind of operator that brings you to the sparse domain of X. So G would be the sparse domain in this for this approximation for this function X. And the way you can view sparse sampling is that L1 the compressive sensing is that the L1 is basically a surrogate for the pseudo norm L0, so you can have a tractable problem, and this parameter lambda, which people like to think of in different ways, but just for all intents and purposes can be thought of as the way you kind of balance how much you trust your data versus how much you believe what you know to be true about the sparsity of the problem. So if you have more confidence in your data, then this lambda would be smaller, and vice versa. Okay, so now, as I noted before, people use L1 regularization for spotlight SAR, and it's pretty effective in some sense, right? So like these are some examples of that. So on the left here, this is an NFFT reconstruction, and in the middle, it's a reconstruction where this operator L it recovers. It's a TV operator, and then on the right is if you just assume the underlying signal itself is sparse. I don't remember the details of how much tuning that was done with the parameters, but this is not a particular hard problem in the world of SAR because you have a lot of information. It's a 360-degree aperture, but anyway, that's the kind of thing that you would see if you did that. We're well aware that of the drawbacks of L1 regularization. There have been many papers written about the lack of robustness for in choosing this parameter lambda in the previous slides. But really, more to the point, it's one of the sort of kind of head scratchers about this, at least to me, when I first started paying attention to this, was that this is a global this is a global measure, right? It's a norm, but really the sparse domain, it's sparse. It's not zero. So I had always sort of thought in my mind that there must be a way that you can better capture the local features in the sparse domain, which would make this approximation more accurate. And so, right, so this is what's put in this third bullet. you really want this parameter lambda from the previous slides to be spatially varying so that the true signal passes through, the true signal in the sparse domain passes through. So I'm not the only person that thought of this. And in fact, there have been quite a few articles about this in using iterative reweighting methods, where they designed this matrix W, which written this way demonstrates its spatial variation of the parameter lambda from the previous slide of that parameter. So they designed this to try to reflect that there are some local features in the sparse domain that you want to pass through and not penalize. So we played with this for quite a while over the last couple of years, around 2017 or so. And we found that there were some major issues with robustness. And mainly that if you ended up with the incorrect weight, which could very likely happen if you had false information or noise or anything like that, then you're kind of stuck with this bad matrix W. And that later on reinforces more bad information. So it didn't work very well. It's also kind of expensive because you have to do this. You have to recalculate this every time. So we thought, well, what's a better way maybe to do this? And we thought that it's actually better to pre-process to find this matrix W. And the way you want to do that, the way you could take advantage of that is from multiple measurements, because that should tell you the sort of local, the support in the sparse domain, or more specifically, where you don't want to penalize the regularization term. So that's where we were thinking about this. Okay. Right. So this additional information. So what we say is following: we have additional information that's coming from these multiple measurement vectors, which I'll just write from here on as MMV. And I'm using vectors and image values as the same. You could just think of it as one long vector if you like. And the way you want to exploit this information is by using the concept of joint sparsity, which is a very simple notion that if that whatever is sparse from one set of vectors of the measurements in the sparse domain should also be sparse from another set of measurement vectors in the sparse domain, assuming that they're all looking at the same picture. So that seems like a logical thing to do. All right, so just to have the definitions written down here. So we have standard sparsity would be, of course, if J equals 1 here, then you'd have something that's S sparse. So if it's S joint sparse, then you have the cardinality of the union of the supports of these sparse domains, the support and sparse domain. Okay. Right. So that's what we want to exploit now. And the question is how best to exploit it. And so again, we're not the first people to think of this. It wasn't done maybe in this context, but people did use something called joint sparsity a lot in the sampling, in the world of sampling. Ben Adcock and some of his colleagues I know wrote papers on this, and they used this idea of joint sparsity using a 2-1 norm. And when we first started to do this, we compared our work there, and we found that our idea worked better for the kinds of problems we were interested in, both in terms of efficiency, but also in terms of accuracy, and also in terms of, well, I guess this is part of efficiency, that you can do things in parallel. And I'm not going to talk about the L2-1's joint sparse regularization, but I'm happy to talk about that with someone if they're interested in it. But what we said is that this joint sparsity could actually be, you could actually get at this, right? Or more to the point, you can actually get at what is the support in the sparse domain by looking at the variance of the multiple measurements in the sparse domain. All right, so okay, so once you do, and I'll talk about how you do that in a minute. So, right, so the idea is that you figure out where the support is in the sparse domain. Once you figure that out, you can design a good weighting matrix, or, you know, if you want to call it spatially varying parameter for this sparse operator. And the idea is that you so this W is prescribed so that you penalize heavily when it's truly sparse, because that means that you want that to be true in your reconstruction. And you try not to penalize at all when it's not truly sparse, because that would make this untrue. And then you want to rely on your fidelity term in those regions. Okay, so, and what we learn from the variance is that wherever there's a lot of variance, it's likely that that's a place of support in the sparse domain. And whenever the variance is small, it's likely that it's truly zero in that domain. And I want to make one more point, that you really kind of eliminate the need to do L1, because you're kind of masking out the places where there's support. So you're no longer using all the same arguments that you have to use for compressive sensing. You're just saying you want something to be zero. And so there's in a particular region, and then there's no reason you could use whatever norm you want for that. And so 2 is easier computationally. In practice, that's not always the case, because you can have a lot of noise. So that depends on different things that are true to your particular problem. Okay. So there's some benefits to this also in terms of the L2-1 norm, which I'm not talking about today, is that you can do this first thing, or as we say, offline. So we don't have to include the calculation of this matrix W. Once you know it, you know it. So it's not iterative. It's more robust, it's more efficient. And if you're interested, which we're doing work toward this now, if you want to somehow keep the different image, like this just gives you one image, right? Because you just choose one F here, but you can keep multiple images from this as well if you want to hold on to multiple copies of an image. Okay, so how do we calculate this matrix W? So you're using this definition of joint sparsity, and then you look at the variance. Right, so G is how this would be the true variance if you know exactly. Actually, that's not quite true. So this is the variance. So G is the calculated. Yeah, this is not 100% right the way I wrote this mathematically. So G is obviously an approximation, because if G were exact, this variance would be 0. So G is an approximation to the sparse domain, to the vector in the sparse domain from the measurement data. So you look at this variance across the measurements, which is this capital J. And if it's small, that means it's likely that, so there's little variance, that it means, yeah, you're probably at a place where there's, where it's sparse. And if it's large, it means it's a place of support. So that gives you an easy formula for calculating this weighting matrix W, which should be proportional to 1 over the variance, which is really proportional to 1 over the size of the jump. This should be an absolute value. And it has the desired consequence that this L1 regularization term is heavily penalized in sparse regions, but not in regions of support. Okay, I see I'm running out of time already. Mark's going to let me go over. All right, here's a nice little one-dimensional example. So this is an underlying function, and these would be the 2 results if we used L1. So P would be 1 and P would be 2. So this is obviously an eyeball norm picture, but it's nice. So, but to show like how this matrix W is calculated, so remember we have Fourier data. So in the sparse domain, we have these different results from the Fourier data. So that gives us a variance profile like this, and then the weights are inversely proportional to that, which is exactly what you want. You don't want to weigh things. You don't want to have penalize heavily where there's support in the sparse domain. Okay, and here's just the algorithm that we have there. So we're given the Fourier data. We calculate the edges from the Fourier data. We calculate the spatially varying weighting matrix from the edges that come from the Fourier data, and then we do this LP regularization. I have to make some comments because as people who have known me a long time will know that these are important to me. So first of all, if you're talking about a complex signal, the function is not sparse in the complex, in the whole domain. It's only sparse in the magnitude. So you have to so you have to make allowances for that. And what you do is you do something quick and dirty to extract the phase so that you can keep this a linear operator here, right? Because otherwise you don't want to use the magnitude directly in the L1 regularization. I mean, people do it, but it's much more efficient if you do this linear approximation for it. So that's the first thing, because the phase itself is not sparse. It's just the magnitude that's sparse. The other thing, is that this has come up a few times over the course of my career, is that, it's the difference from starting with indirect data versus direct data. In our case, the indirect data being the Fourier data. So if you first try to do a reconstruction of that underlying function or image from the Fourier data and then try to calculate edges, there's potentially quite a bit of data loss, because there's noise in the data. You're probably getting rid of information from the high frequency modes, and it's those high frequency modes that actually carry the most information about the edges. So it's really what we found, and this actually makes a difference, is that for this G, you calculate using what we call this concentration factor method, but there are other things to do, of course. Dicha is on the call, and he worked a lot on this as a graduate student. But anyway, but the point is that it matters. You shouldn't try to reconstruct first and then find the edges. You should find the sparse domain as much, the values in the sparse domain as much as possible from the indirect data. And so here's just the method that we used to do that. Okay. So here's some results, and at first glance, this doesn't look very impressive until I tell you, hopefully, that something that will make you be more impressed. So this is this technique that we use, and this is complex data, and we have different values, different scenarios that we used here in each of these little plots. So A is just if you just do back projection. So B is this thing we call high order total variation, which I'm not talking about today. C and D, C is just a filtered reconstruction. D and E are both different variations of a variational approach that people use sometimes to get rid of speckle. And F is the result of this new method. Now, note in this new method, for this particular problem, we only use 2. So J is 2. So we're not having tons of multiple measurements. So you might look and say, there's not really that much of a difference between B and F. Okay, fair point. Except with B, we had to do a ton of tuning on the parameters to get this image, whereas F, everything was tuned right away by using the variance of these 2 data vectors. So that's the sort of take-home message from that. Okay, so right. So to sort of sum up what we did and to move into what we're trying to do now is it turns out that it's true that if you have this redundant extra information, you can improve the robustness and efficiency of standard compressive sensitive algorithms by using this variance calculation. But it's still only a point estimate. So you can't possibly quantify the uncertainty from a point estimate. And in the applications, more and more in the applications people are interested in, we really do want to be able to understand what the amount of uncertainty is, because you have to make decisions based on how likely you are to be correct or incorrect about something. So we're interested in having some kind of uncertainty quantification for this.
Can I ask a quick question?
Of course.
In your experiments from before, you were minimizing the TV norm, or you were finding edges and then sort of doing an edge-based reconstruction, assuming it was smooth after removing the edge data, or what?
Not exactly. So what we did, so this G here from the edges is just to find this vector, this matrix W.
Okay, I see. And then
yeah, and then this L, depending on the application, we use different L's. Like, for example, in this application, because of the variation of the underlying function, we used a higher order total variation of second order. So it depends. That's application dependent. In the SAR problems, you typically TV is fine, assuming that you remember to extract the phase. If you don't extract the phase, you get nonsense.
Okay. All right.
Answer. Okay. All right. Right. Okay. So we thought, all right, this is pretty good, but we want to do some uncertainty quantification. So to do that, we're going to set up our framework in this using a Bayesian approach. Right, and I think someone asked earlier if these are assumed to be independent, and I kind of, yes, and they are. Okay, and so here's the model. It's the same model as we already discussed already. And you can use compressive sensing algorithms for some particular set of observations that you would have. But so now instead we're going to use the Bayesian approach. So here's so here's a Bayes formula. This lambda is related to, but not the same lambda as was in the compressive sensing. So hopefully there's no confusion there. Okay, so right, so what we need to do is we need to find a corresponding likelihood and a corresponding prior, and the prior here involves this hyperprior parameter. So we didn't spend much time on the likelihood. Just if noise is given in this way, if it's Gaussian, and I'm only talking about real problems now, although it should work for complex problems. We just started with real problems. So we started with this likelihood, right? I'm sorry, we started with additive Gaussian noise. So that gives us this likelihood. So for the prior, we included a hyperprior term here, and I'll get to that in a minute. And then we don't consider this evidence at all in the denominator, because all it does is normalize this distribution, and that's fine. We don't need it for our application. And we know it's non-zero in our application because otherwise the observation itself would have probability 0. Okay. Yeah, so I already said we're not going to focus on the likelihood. You might want to do this because you could have different types of data that you might want to weigh in different ways. And so there's a whole slew of problems to discuss, but just to start out, we didn't consider it. So the main purpose of this talk, 45 minutes in, 47 minutes in, is constructing a good prior, right? And that's and we borrow from our sort of intuition on this MMV stuff for compressive sensing for constructing this prior. And so in the same way that we thought about compressive sensing, we say, well, sure, there's a sparse. We could make the prior that the underlying image is sparse in the sparse domain, but we actually maybe know more than that. We know that there are we know maybe we can recover where the support is in the sparse domain. And so that's more information that we could put into the prior, which will hopefully yield a better distribution, a more accurate distribution. So, so much in the way that we worked in the compressive sensing, we want to do a spatially informed prior that will hopefully give us more accuracy. And of course, this is empirical because we're using information from the data to arrive at that. And what we found is that, and which we'll show in these next slides, is that our intuition proved correct, that if you use support-informed sparse priors, you get less uncertainty in the homogeneous regions than if you would have typical Laplace priors. And that might actually help the way we do other things, like maybe you'll say, oh, I want to interrogate this region in the domain more because I know there's more uncertainty in this region, or there's less uncertainty in this region, so I don't really have to worry about collecting information there. So we hope that the benefits are important. Okay, so this is the posterior. We already said that what we were going to do about the likelihood. So let's just now talk about the prior itself. And so we'll just sort of get rid of how we deal with the hyperprior first. And much like people do in other kind of machine learning applications, we use k-fold cross-validation, which probably people should use anyway, even if they're doing compressive sensing, because it's a way to sort of parameterize the bias variance trade-off. So this is a standard technique, which I'm happy to show you the algorithm, or you can find on Wikipedia, that you can, so the idea is that you make the prior concentrated, concentrating the density on the value lambda hat that comes out of this k-fold cross-validation. And as I already said, and what's written here is that this is probably a good lambda to use in your standard L1 regularization if you know nothing else, because at least then you have some reason to choose that lambda. Okay, but so now we have this hyperprior. So that what we're left with computing now is what we're calling the support-informed sparse prior. So what are our assumptions that we want to put into this prior? First is that, well, there's sparsity in some transformation of the random variable x. This is the unknown that we're trying to recover. And the other is that we have multiple observations of this y, which allows us to sort of know something more about where the support is in the underlying domain. And much as I talked about, in the same way that I said before, that you probably don't even have to have multiple observations. You can just process things in multiple ways. You can relax the assumption, although that was not the focus of what we did, so I'm not including that here. Okay, so before we talk about how we're going to do this support-informed sparse prior, we'll just throw out a standard sparse prior, which is Laplace prior, and I'm just using it here because it's commonly used in compressive sensing. But our method doesn't depend at all on what type of sparse prior you use. You can use spike and slab, horseshoe. I got a whole earful of different priors from a bunch of statisticians lately, and I'm woefully I lack a lot of knowledge in this region, but I came out of it thinking it doesn't really matter. Well, don't tell them that, but it doesn't really matter for our purposes what you choose as your sparse prior. The point is that it doesn't tell you anything about the support in this form. Okay, so yeah, and just to sort of make sure this point is well established, is that it doesn't really matter. It's good to choose the hyperparameter well, but that has nothing to do with this support in the sparse prior. So you still have this sort of global effect from this prior. So so you want to do something so that you have a spatial variance, just like we had before, because as written, it doesn't take into account the the locations of support. And we want to use, again, we want to use this idea of joint sparsity to obtain this information so we can design a better prior. So we play the same game, right? We say, this would be basically G tilde from my previous slides coming from the Fourier data. That's the difference. And it's a little mistake that I made here. Okay, so you find the variance from the multiple measurements in the sparse domain. And then you say the same thing again. If it's a lot of variance, you probably are at a place of support. If there's less variance, you're probably at a place where it's truly sparse. And so what you do is you want to and what we did in the compressive sensing case is we made the scale of this weighting parameter based on this variance. And then we enforce the prior heavily in sparse regions, and we don't want to enforce it in where there's actual support. Okay, I see that I'm running out of time. So we do something similar here, except now we just make a mask. We don't use the sparse prior at all, where we think the function is not sparse, because that would be an incorrect prior. And that's really the bottom line. So here's a function that we choose to, so hopefully that's sort of the bottom line. You don't use a prior where you don't think the prior is true. That sort of makes sense, right? So here's the underlying signal that we're taking. We got this from a paper by Bardsley, so we used the same example. We looked at 4 different points here. So this is a large jump, a small jump, a region of smoothness, also a region of smoothness, except more variation. So if you follow this procedure to find this support-informed sparse prior, you realize that you should not be enforcing the prior at these 2 points, because it's not sparse in this, it's not sparse in the sparse domain, but these are sparse in the sparse domain, so you should be enforcing them there. Okay, and that's the algorithm that you use to get the support-informed sparse prior. So you find this this weighting matrix, if you will, using the variance, and then you make a mask according to it. So it's 0 wherever there's support, and it's non-zero wherever there's no support. I don't think we need that. Okay, so that leads to these different choices of posteriors. Okay, so this would be a sort of standard posterior. This would be our support-informed L1 posterior. So we put a mask here, and we use L1. This is another sort of, I guess, standard type posterior, but using L2. And then this would be a support-informed L2, which means that you only apply this where it's truly sparse. Okay. And if you want to look at the map estimate, you see by simple calculation that you get back to exactly where you started with compressive sensing. So using this MMV stuff. So it's pretty much the same as what we did. So this is the map estimate that corresponds to the compressive sensing result we got using the MMV. All right, so we use Metropolis Hastings because there's no closed form. The version of MCMC, this is just sort of standard stuff about MCMC, what the acceptance ratio looks like, burn-in rate, total length of the chain. So here are our results in 3 minutes, according to Mark's microwave. Sorry that these have meaningless numbers to you because they come from the paper we just wrote, but ours in this picture is the blue. And this is the L1 version and the L2 version. So you can see that for a sparse signal, this is a confidence interval. So you can see we have far less uncertainty actually in the full domain. This is SNR 0. This picture is, I think, pretty telling. So these are both support informed. The solid is the L1 and the broken is L2. And what it says is where it's actually truly sparse and where it's actually not truly sparse in the sparse domain. So where it's truly sparse, it's okay to use the standard L1 or L2 prior, because especially when there's a lot of noise, because in those regions it's really sparse. But you get a pretty big error even at SNR, say over here at 2, if you try to use the incorrect prior, where it's actually, not sparse. Okay, so these are corresponding confidence intervals. We didn't do the L2 sort of standard prior in this case. It was hard to compute, and we could do other things, but we just decided it wasn't working very well anyway, so we let it go for a lot of noise. Okay, so this picture I think is quite interesting. These are these 4 points in the domain. So this is the big edge, the small edge, the really flat area, and the where the Gaussian kind of thing looks at on the right hand side of that figure. This part here. And these are the resulting distributions that you get. This is for less noise and more noise. So I think the most important one to look at is the blue and the red. So the blue would be our support informed, and the red would be without the support informed. And you can see like how we, especially where there's a large jump, right? It's clear that you should use the correct prior there. And even in the small jump, it makes a difference. There's very little difference in the smooth region. And then, but then again, it starts to matter when when it's truly smooth. So those are interesting results, I think. These distributions are not, like we wrote down in our paper what these distributions are that you get from from here. They're not Gaussians, but you can see what they look like. Okay. These are the acceptance ratios, just to show that in fact you get between 0.2 and 0.8, which is acceptable. So this is I'll end in pretty much here. So this is the autocorrelation function plots. So you want this to converge to 0, right? This means that the chains are not correlated after a certain amount. This is the lag length. And so ours again is the red. So you want to compare really the red and the blue. So we converge a lot faster. This is more noise. I'm sorry, the bottom is more noise, the top is less noise, and it's for these 4 points across again. This is a trace plot, so you can see, where we are around the mean. And then these are, again, show you, this is the overall error. And look, really, this is significant. Where there's a true edge in the sparse domain, using the standard prior is really a bad idea there as you increase the noise. It's also true in the small, where there's a small edge, and it matters less in the smooth regions. These are all important things to know. Okay, so that's where we're going. That's what we did. Where we're going is we want to, now move to complex signals and sort of data fusion projects, and that's pretty much it. Thanks very much.
All right, thanks a lot for the talk. I'd like to open it up now for questions if people want to post questions in the chat, or just unmute yourselves and ask. Feel free.
Excuse me.
So